When dealing with rigid bodies, we have a couple of equations we can use to calculate angular momentum and torque. L equals I omega and torque equals I alpha. However, these equations do not hold in general for rigid bodies. They only hold under particular conditions. Similarly, just looking at the component of these vectors of either angular momentum or torque along the axis of rotation, for an example, suppose it is the z-axis, results in certain equations, Lz equals I omega z and torque z equals I alpha z. But these also are not always true. So when are they true? This video will seek to clarify the exact conditions when you may use these equations, when these equations are true. In brief, they are true when we make simplifying assumptions concerning the axis of rotation about which we are computing these quantities. We first have to assume that the body is purely rotating about the rotation axis. We are not in a frame of reference in which the body is translating, just rotating. Mathematically, this means that each point on the rigid body has a total velocity of omega cross r. And this also means we are in a reference frame in which the rotation axis is fixed in location. The rotation axis has no translational motion. This also means that each point on the rigid body is just moving in a circle about the rotation axis. There is a special scenario, namely when we have an axis through the center of mass, and in that case, if the axis of rotation is translating, even if it is accelerating relative to some inertial reference frame, then if we change to a reference frame that moves with the center of mass, then the rigid body will still be undergoing pure rotational motion about that axis, because the translational motion will disappear when moving into a frame that translates with the same velocity, which could be accelerating, as the center of mass. This just emphasizes the importance of reference frame when thinking about a rotation axis being fixed in location. It must be fixed in location in the reference frame that we are interested in, but relative to another reference frame, it could move. And if the axis is through the center of mass, it could be accelerating relative to another reference frame. Or in other words, if the axis of rotation is through the center of mass, then the reference frame that moves with the center of mass may be non-inertial, and the body will still be purely rotating about the center of mass, so L equals I omega and torque equals I alpha are true. We also make the assumption that the rigid body is rotating about a single axis. That is, the rotation axis, the angular velocity, does not change direction, because in this case, the angular velocity will only have one component, which also means there's only one single rotation axis. Or to put it another way, we assume that the rotation axis is fixed in direction. The direction of the rotation axis is not changing in the reference frame of interest. If it does change direction, if angular velocity has more than one component to it, if there is rotation about more than one axis, then we will get precession, and the equations will not generally be true. And by not generally true, I just mean you can't apply them all the time to all the different scenarios that you run up into. They can work sometimes, though they require a bit of a nuanced understanding of them. And they could also be true for a moment as the object is rotating. So as the object rotates, the axis might align in a good direction, and the equations could hold momentarily, just for an instant. You might also have a question here, though, about precession and applying the equations of motion to them, because in precession, as already noted, the axis is changing direction. Well, what's usually done there in introductory courses is that an approximation is made, and the approximation is made so that the angular momentum can be calculated along the spin axis using these equations. See your textbook or course on the subject of precession for more information on this point. Altogether then, so far, we are assuming a fixed axis of rotation, so an axis that does not move or change direction relative to the body, relative to an inertial frame. Or, if the axis is through the center of mass, then the axis can be translating with acceleration, but it must stay fixed in direction. Finally, for L equals I omega and torque equals I alpha, but not for their component forms, the Lz equals I omega z, the torque z equals I alpha z. But only for L equals I omega and torque equals I alpha, the full vector, not just a component of them, we must also assume that the rotation is about a symmetry axis through the center of mass, Or if the axis is not through the center of mass, then the axis must be parallel to a symmetry axis that is through the center of mass. That is, we need to assume the conditions that make angular momentum and angular velocity point in the same direction that allow us to treat the moment of inertia as a scalar. Technically, this symmetry axis through the center of mass is called a principal axis. So we are either looking for a rotation axis that is a principal axis, or if the axis is not through the center of mass, the axis needs to be parallel to a principal axis, or another way to put it, it must be in the principal direction. See the video on moment of inertia for more details about this assumption. As I've already stated a couple of times, when we talk about a rotation axis being fixed, we need to consider reference frames. So whether it's fixed in location or direction or both, we need to think about reference frames. So let's clarify that, although I will be repeating myself a bit. So firstly, if the axis is not through the center of mass, the rotational axis must be fixed relative to the body and to an inertial reference frame. The inertial reference frame in which it is fixed must be the frame in which you are calculating the angular momentum or the torque. Non-inertial reference frames for axes through points that are not through the center of mass makes the equations not always true. They won't always be true in such cases. If, however, the axis is through the center of mass, then the equations are true even if the axis is fixed in a non-inertial reference frame. So for an example, consider a frame that is translating with the center of mass, even though that frame accelerates relative to a different inertial reference frame. Then, this reference frame that's translating with the center of mass is a non-inertial reference frame. So long as the axis is still fixed in direction, then the equations hold true. Of course, if you are in this reference frame, then the axis will be fixed in location in this reference frame. It will not be translating. But it's very key that the axis still does not change direction. In any reference frame, that must not be the cause of the non-inertial reference frame. What this means, though, is that the center of mass may be accelerating, and the equations will still hold true, so long as the axis is through the center of mass. We also need to make assumptions about the location of the reference point about which angular momentum and torque are calculated. In all cases, the reference point is on the axis of rotation. But remember, the axis of rotation is an infinite line, so what point on the axis of rotation should the reference point be? So for an example of what I'm talking about, here's a cylinder rotating about the red rotation axis. Should my reference point be here? Should it be there or there? All of these points are on the axis of rotation. Where does it need to be so that the equations are true? The first thing then is, if the axis is through the center of mass, it turns out the reference point can be anywhere on the axis. So for example, I've already drawn something like this. The red line, the axis of rotation that I drew, is going through the center of mass, and I can put the reference point anywhere on the axis to calculate angular momentum and torque about that point, and the equations will be true. For the full vector equations, if we have the axis through another point, then the reference point must be level with the center of mass. Mathematically, that means the reference point must be in a plane with the center of mass that is perpendicular to the axis of rotation. So for an example, considering this cylinder again, which is now rotating around this green axis that is not through the center of mass, where should the reference point be? Well, the center of mass is over here. My reference point should be here. It shouldn't be here. It shouldn't be here, because this point right here is in a plane that contains the center of mass, and this plane is perpendicular to the axis of rotation. This point up here, you could find a plane which contains it in the center of mass, but it is no longer perpendicular to the axis of rotation. So practically speaking, this means just consider an axis that's through the center of mass, and then imagine translating it to the axis of interest. And wherever the center of mass was, that's where your reference point needs to be on the translated axis. However, if you are not interested in the full vector of angular momentum and torque, if you're just interested in one component, those equations are less restrictive. If the axis is through another point, then you can put the reference point anywhere on the axis. So I could put it here or here. And those equations for the z components, for the components along the axis of rotation, will still be true. In summary then, for both sets of equations, we have two cases. For the full vector equation, they are only true when calculating them in a reference frame in which the rigid body is undergoing pure rotation about an axis, that is fixed in direction and along a symmetry that is principal direction. If the axis is through the center of mass, then it must be a symmetry or principal axis. Considering our cylinder again, here's an axis through the center of mass. It's a symmetry axis. Here's an axis through the center of mass. It is not a symmetry axis. The kind of symmetry will be discussed more detail in the moment of inertia video, but the idea is that it is a rotational symmetry where the object looks balanced on all sides. So here's one, here's two, and then there's a third one going through the page. But in any case, the axis through the center of mass needs to be a symmetry axis, and if it's going through the center of mass, then the axis needs to be fixed in direction. It can be translating relative to another reference frame, but not rotating or precessing, because you can always go to a reference frame in which the object is purely rotating, a reference frame that's traveling with the center of mass. And in that case, the reference frame, even if it is non-inertial, even if that reference frame is accelerating relative to another reference frame, then these equations will be true. The axis just needs to be fixed in direction relative to any reference frame. The reference point can be anywhere on the axis also. The other case is an axis that is through another point, not the center of mass. Using the cylinder example again, here's an example of an axis that is not through the center of mass. In such a case, the axis needs to be parallel to a symmetry or principal axis. So here's the symmetry axis, the principal axis. This red axis is parallel to the green axis. If instead I tried to find an axis of rotation that was not parallel to any of the symmetry axes, then the equations would not be true. So the equations are only true if the axis is parallel to a symmetry or principal axis that is going through the center of mass. In this case, the axis must be fixed completely. It must not rotate, it must not translate. The axis must be fixed both in direction and location, and it must be fixed relative to the body and to an inertial reference frame in which you are calculating the angular momentum or torque. So the reference frame in which you calculate angular momentum or torque must be an inertial reference frame. That means the axis could be translating relative to another reference frame, but the translation must be constant velocity. So that way the reference frame in which the axis is not moving is still an inertial reference frame. As for the reference point, it still must be on the axis, but now it can't be anywhere. It must be in a plane perpendicular to the axis that contains the center of mass. So you can think of it as being on ground level with the center of mass, not above or below, which we talked about before. So there's your reference point. Here's the plane containing the reference point and the center of mass, and it is perpendicular to the axis of rotation. Meanwhile, if you are only interested in calculating the component of angular momentum or torque along the rotation axis, then you can drop the assumption about symmetry or principal direction. Instead, the equations are true for a pure rotation. The equations are true in a reference frame in which the rigid body undergoes pure rotation about an axis that is fixed in direction. There are likewise two cases which mirror the previous. The axis, if it is through the center of mass, then it doesn't have to be a symmetry one, but the reference point can be anywhere on the axis, and it must be fixed in direction. It likewise can be translating relative to another reference frame. It could be accelerating relative to another reference frame, and therefore could be inertial or non-inertial, but the axis must still be fixed in direction relative to any reference frame. If, however, the axis is through another point, then the axis must be fixed. It must be fixed relative to the body and to the inertial reference frame in which you are calculating these components of angular momentum and torque. The reference frame can still be anywhere on the axis. The reference point can still be anywhere on the axis. So there you go, that's the summary. In brief, the full vectors require an axis fixed in location, that is pure rotation, fixed in direction, and must be a symmetry axis or parallel to it. Meanwhile, the component forms require the fixed axis still in direction and location, but symmetry can be dropped. And if the axis is through the center of mass, the reference frame in which you calculate these quantities can be non-inertial. That reference frame may be accelerating, the center of mass may be accelerating relative to another reference frame.